There's just something deeply comforting about the sound of a boiling pot of water.
Oh, absolutely. Yeah.
Whether you're like making pasta, brewing tea, or maybe you're out camping and trying to make river water safe to drink, we just have this ingrained, almost instinctual belief that bubbling, rolling 100 degrees Celsius water is the ultimate cleanser.
Right. It feels like a fundamental rule of survival, Fire equals heat, heat equals destruction, so boiling water must equal absolute sterility. It's an intuitive sense of safety.
It feels like a law of nature. But if you step into a microbiology lab or a hospital sterilization wing, or, well, even just look closely at the instructions for home canning vegetables, you realize that comforting bubbling sound is actually hiding a massive blind spot.
A really dangerous one, yeah.
Yeah, that pot of boiling water is basically a biological safe haven for some of the most resilient organisms on Earth.
It's the great illusion of basic chemistry, and honestly, shattering that illusion is what ultimately gave us the foundation of modern medicine and infection control.
So welcome to today's deep dive. We're exploring the really fascinating high-pressure world of autoclaves and the science of steam under pressure.
Yeah, and we've got a great stack of sources today.
We do. We're covering microbiology, some intense historical scientific rivalries, and the core physics of sterilization. Our mission today is to understand exactly how heat and pressure work together to sterilize equipment, why your boiling kettle is surprisingly terrible at killing certain germs, and how a 19th century lab invention became the invisible backbone of modern medicine and food safety.
It's a journey.
It really is. And I can promise you, the listener, the next time you open a can of soup or sit back in a dentist chair, you're going to have a profound new appreciation for what it actually takes to make something truly, absolutely sterile.
Because the gap between just being clean and being sterile turns out to be exactly 21 degrees Celsius.
Okay, let's unpack this. We have to start by dealing with this everyday misconception we just brought up. Walk me through the physics here. Why is boiling water not enough to guarantee sterility?
Well, it comes down to a strict limitation of water at sea level. At atmospheric pressure, water boils at 100 degrees Celsius.
Right.
And the crucial mechanism to understand is that once water reaches that boiling point, you hit a thermal ceiling. No matter how high you turn up the stove burner, the liquid water itself will never get hotter than 100 degrees.
Wait, really? Even if I leave it on a roaring fire for like an hour, the temperature of the water just flatlines?
Not a fraction of a degree higher. Yeah.
It's wild.
It is. Any additional thermal energy you pump into that pot isn't raising the temperature. It's entirely consumed by the latent heat of vaporization.
So it just makes more steam.
Exactly. The energy goes into breaking the bonds between the water molecules, converting the liquid into steam faster. You just get a more violent boil, but the temperature stays locked at 100.
Now, 100 degrees is obviously pretty hot. I assume it handles the everyday threats just fine, right?
Oh, absolutely. I mean, it will easily destroy active vegetative bacteria, most viruses and parasites.
So for making tap water safe to drink in an emergency, it works.
Right, it works for that. The problem arises when you encounter bacterial endospores.
Okay, these are the survival pods, right? The dormant state some bacteria enter when things get rough.
That's a really good way to visualize them. When certain bacteria face starvation, extreme heat, or chemical stress, they pack their DNA into this incredibly tough, highly dehydrated armored shell.
Like a microscopic bunker.
Exactly. And these endospores essentially just shrug off boiling water. In the late 19th century, scientists were actually documenting endospores surviving in boiling water for over 20 hours.
20 hours. You could boil a pot of water from sunrise to sunset, and these things just sit there, perfectly intact.
Waiting for the water to cool down so they can reactivate.
Which is a terrifying thought if you're trying to perform surgery.
Or preserve food, yeah. So to get past this 100-degree thermal roadblock, we use the autoclave. It's a sealed vessel. By locking the chamber shut and trapping the steam as the water boils, you increase the density of the gas molecules inside.
Which raises the internal pressure.
Right. A standard autoclave cycle pushes the pressure to 15 pounds per square inch above atmospheric pressure, so about 2 atmospheres total.
And because the pressure pushing down on the liquid is heavier, the water molecules need more energy to escape into the air as steam.
That's the core physics of it. By increasing the ambient pressure, you physically force the boiling point of the water up. At 15 psi, water doesn't boil until it hits 121 degrees Celsius.
And that jump from 100 to 121, that extra 21 degrees is the entire game. That's the kill zone.
It really is.
But I'm curious about the actual mechanism of death here. What is happening to the microbe at 121 that wasn't happening at 100?
Well, lethal heat kills microorganisms by denaturing their proteins and nucleic acids.
Yeah.
Proteins are these complex, three-dimensional structures folded in very specific ways.
Right.
If those molecular folds unravel, the structure fails. The cell walls collapse, the metabolic enzymes stop working, and the organism dies.
It sounds a lot like cooking a raw egg white.
How do you mean?
Well, when it's raw, the proteins are folded in their natural state, and it's clear and liquid. But when you apply heat, those proteins unravel, they tangle up with each other, and it turns into a solid, opaque mass. And once it's tangled, it's permanently non-functional. You can't uncook an egg.
What's fascinating here is that that's a very grounded way to look at it. You cannot fold a denatured bacterial protein back together. But the vital detail here isn't just the heat, it's the moist heat.
The steam itself.
Yeah, the steam itself is doing a lot of the heavy lifting. Moist heat is dramatically more efficient at denaturing proteins than dry heat.
I always found that confusing, honestly. Isn't heat just thermal energy? Why does the presence of moisture change how the heat damages the cell?
It's because of how water behaves at the molecular level. Water molecules are highly polar, meaning they have a slight electrical charge.
Okay.
When steam penetrates the bacterial cell, these polar water molecules actively interfere with the hydrogen bonds that hold the bacterial proteins in their complex 3D shape.
Oh, I see.
The moisture essentially acts as a chemical shortcut, disrupting the structure and making it much easier for the thermal energy to unravel the protein.
So the steam is actively participating in dismantling the bacteria, not just delivering the heat.
Precisely. To put that in perspective, if you wanted to sterilize medical instruments using just a dry heat oven, no steam, just hot air, you would have to crank the temperature up to 160 or 170 degrees Celsius.
Wow.
And you'd have to leave the instruments baking in there for 2 hours or more.
Because dry air doesn't have that chemical shortcut. So it takes 2 hours at 160 to do what an autoclave can do at 121 in just 15 to 20 minutes.
Yeah, it's a massive difference in efficiency. Moisture is the ultimate catalyst here.
So we have this sealed high-pressure steam chamber, but I know science rarely jumps straight to the perfect solution. How did we actually figure this out? Did someone just start sealing boiling pots to see what would happen?
You know, the initial invention had absolutely nothing to do with science or sterilization. Yeah, the direct mechanical ancestor of the autoclave is the steam digester, which was invented way back in 1679 by a French physicist named Denis Papin.
Wait, 1679? That is well before anyone understood germ theory or even knew what a microbe was.
Yeah.
What was he trying to do?
He just wanted to cook a better beef stew.
You're kidding?
No, seriously. Papin built a sealed iron pot with a rudimentary safety valve to cook tough cuts of meat faster and extract marrow from bones. It was basically the world's first pressure cooker.
That is wild. The pressure cooker was invented to make dinner faster, and it just sat around in kitchens for 200 years before microbiologists realized they could use the exact same physics to destroy invisible pathogens.
It's a great example of a technology waiting centuries for its most critical application. That application finally emerged in 1879 inside the laboratory of the famous microbiologist Louis Pasteur.
Okay, Pasteur, I know that name.
Right, and one of his colleagues, Charles Chamberlain, was dealing with a deeply frustrating contamination problem.
Let me guess. They were trying to grow specific bacterial cultures, but the broths kept getting contaminated by outside microbes.
Exactly. They needed perfectly sterile culture media like a biological blank slate to prove their theories about disease. But the liquids they were boiling kept sprouting unintended bacterial growth.
And I'm sure that wasn't just a mild annoyance for them.
Oh, it was a professional crisis, mainly because of Pasteur's great rival in Germany, Robert Koch.
Ah, the Pasteur-Koch rivalry, the heavyweights of early microbiology.
It was an intense competition, and Koch's laboratory was the one that definitively proved that certain bacterial endospores could survive boiling water. Koch published experiments showcasing spores outlasting those 20-hour boiling marathons.
Ouch.
Yeah, he was essentially demonstrating to the scientific community that Pasteur's sterilization methods were fundamentally flawed.
That must have sent Pasteur's lab into an absolute panic. They had to find a way to kill something that boiling water couldn't touch.
It forced a wave of rapid innovation. Koch's team built their own steam chamber in 1881. Meanwhile, a physicist named John Tyndall proposed a workaround method called Tyndallization.
Tyndallization, what did that involve?
It was an attempt to trick the spores, essentially. You boil the liquid to kill the active bacteria, then let it sit at room temperature for a day.
Okay.
The theory was that the surviving spores would sense the drop in temperature, assume the danger had passed, and germinate into vulnerable vegetative cells. Then you boil it again the next day to kill that new batch.
Oh, I see.
And you repeat it a third day just to be absolutely certain.
Boil, wait a day, boil, wait a day, boil. I mean, that sounds like a logistical nightmare for a busy laboratory.
It was incredibly tedious, and more importantly, it often failed. The germination triggers for spores are complex. Some just remain deeply dormant and completely ignore the temperature shifts.
So they needed a brute force method.
Exactly. So Chamberlain, working under Pasteur, looked back at Papin's old steam digester. He designed a reinforced, pressurized vessel that could safely build up steam pressure without exploding.
And the name autoclave comes from this design, right?
Yes, from Greek and Latin auto meaning self and clavis meaning key, it was a self-locking vessel.
Self-locking.
Yeah, as the pressure built up inside the chamber, the physical force of the steam pushed against the seals, making them tighter. The higher the pressure, the harder it locked itself, which was a vital safety mechanism to prevent the lid from blowing off under 2 atmospheres of pressure.
Yeah, I'd imagine keeping the scientists in one piece was a pretty high priority. Now, I want to circle back to these endospores for a moment because we keep talking about how tough they are. What is actually inside this microscopic armor that allows it to survive a 20-hour boiling bath?
It's honestly a masterclass in biochemistry. The core of the spore, where the DNA is stored, is severely dehydrated.
Okay, so less water inside.
Right. And without water, standard thermal degradation happens much slower. But the real secret weapon is a unique compound called dipicalinic acid, which bonds with calcium ions.
And how does that combination protect the DNA?
Well, the calcium dipicalinic acid complex forms this dense, crystal-like lattice inside the core. This lattice physically binds to any remaining free water molecules, immobilizing them so they can't participate in damaging chemical reactions.
Wow.
It also intercalates or slots directly into the structure of the DNA itself, physically shielding the genetic coding from heat and radiation.
So it's literally structural reinforcement at the DNA level.
Exactly. You combine that with a dense outer coat of highly cross-linked proteins, and you have a biological structure that strictly requires 121-degree pressurized steam to penetrate and dismantle.
Okay, so Chamberlain builds his autoclave. The high-pressure steam breaches the spore's armor, disrupts the calcium lattice, denatures the proteins, and the spore dies. But in a modern hospital setting, how do we actually know it worked? I mean, Chamberlain might have been satisfied if his broth stayed clear, but today we need absolute certainty.
We achieve that certainty through rigorous mathematical modeling and biological testing. In microbiology, we measure heat resistance using the D value.
D value.
Yeah, this is the specific amount of time required at a given temperature to kill 90% of a microbial population.
A 90% kill rate, so leaving 10% alive, which then gets reduced by another 90% in the next interval.
Exactly. It's a logarithmic scale, a 1-log reduction. And the gold standard organism we use to validate autoclaves is the spore of a bacterium called Geobacillus stereothermophilus.
That sounds like something that actively enjoys the heat.
It really does. It's a thermophile. Its spores are among the most heat-resistant biological structures we know of. At our target temperature of 121 degrees Celsius, its D value is roughly 1.5 to 2 minutes.
So every 2 minutes inside the autoclave, 90% of these ultra-tough spores are destroyed. And since the standard cycle is 15 to 20 minutes.
You achieve what we call a 12-log reduction. It drops the population by a factor of 10 to the 12th power.
That's a huge number.
It is. To put that in practical terms, you could put 1 trillion of these highly resistant spores into the autoclave, and by the end of the 20-minute cycle, statistically, less than 1 single spore would survive.
1 trillion down to basically 0. That is definitively dead. But I have a huge question about how hospitals verify this on a daily basis. I'm thinking of that beige tape with the diagonal stripes. You see it on wrapped surgical trays all the time.
Oh, yes, the indicator tape.
Right. The stripes turn dark brown or black when it comes out of the autoclave. Doesn't that prove it's sterile?
If we connect this to the bigger picture, that tape is actually the source of a very dangerous misconception. Relying on it as proof of sterility is a massive trap, and it has genuinely led to documented infection control failures in clinical settings.
Wait, really? If the tape turns black, doesn't that mean the autoclave did its job?
Not at all. Autoclave tape is merely a chemical indicator. The ink just reacts to heat. All it proves is that the exterior of that wrapped package reached a certain temperature at some point during the cycle.
Oh, wow. It's exactly like a turkey pop-up timer. When the
Yes.
little red stick pops up, it just means the air in the oven or maybe the surface of the bird got hot. It tells you absolutely nothing about whether the stuffing deep inside the cavity is actually cooked and safe to eat.
That is an unsettling but highly accurate comparison. If you just trust the pop-up timer, you could give your family salmonella. In a hospital, an autoclave might heat up, the tape changes color in the first few minutes, but what if the cycle is aborted early? Or, far more commonly, what if the steam fails to penetrate the center of the surgical tray? If the steam doesn't physically touch the scalpel, it isn't sterile, regardless of what the tape on the outside says.
So if the tape is just giving a false sense of security, what is the actual proof? How do they know the steam actually reached the instruments?
The only true guarantee is a biological indicator. Hospitals take small vials or strips of paper inoculated with live Geobacillus stérothermophilus spores, and they bury them deep inside the most difficult-to-reach areas of the surgical packs.
Inside the packs.
Yeah, they run the cycle, retrieve the spores, and then try to grow them in a lab incubator. If nothing grows, you have undeniable biological proof of death.
You essentially have to plant the toughest microbe in the hardest-to-reach spot, assassinate it, and produce the body to prove the machine works.
Exactly. And the challenge of getting steam into those hard-to-reach spots is why modern hospitals have largely moved away from older gravity displacement autoclaves in favor of pre-vacuum models.
I always assume steam just fills whatever space it's in.
Yeah.
Why is getting steam into a surgical pack difficult?
It's a problem of fluid dynamics. In a basic gravity displacement autoclave, steam is pumped into the top of the chamber. Because steam is lighter than the cooler air inside, it pushes the dense air down and forces it out through a drain vent at the bottom.
Steam goes in, air gets pushed out. Seems pretty straightforward.
It works fine for open beakers of liquid,
Uh-huh.
but if you have tightly wrapped surgical instruments, porous fabrics, or tools with hollow lumens, like a catheter tube, the ambient air can get trapped inside the folds or the tubing.
Oh, I see.
Air is an excellent insulator, so you end up with these microscopic trapped air pockets where the steam simply cannot reach. The gauge on the machine reads 121 degrees, the tape turns black, but inside that trapped air pocket, the temperature never reaches the threshold to kill the spores.
The air essentially forms a protective bubble against the steam.
Yes, that's why pre-vacuum autoclaves were developed. They use a powerful mechanical pump to violently evacuate all the ambient air out of the chamber, creating a deep vacuum before any steam is introduced.
Well, that's smart.
With no air left to block the way, the steam instantly rushes in and penetrates every tiny crevice, tube, and fabric fold in a fraction of a second.
That makes perfect sense.
Yeah.
Okay, so we've established this gold standard. 121 degrees, 15 CI, for 15 to 20 minutes using a vacuum to ensure total penetration.
Yeah.
That annihilates everything, even the armored spores. But here's where it gets really interesting, because the definition of sterilization used to be simple.
Yeah.
Kills all bacteria and their spores.
It did.
But in recent decades, science had to completely move the goalposts. It turns out, our gold standard doesn't kill everything.
It was a very humbling realization for the scientific community. The entity that forced us to rewrite the rulebook was the prion, which gained global attention in the 1980s and 90s with diseases like bovine spongiform and encephalopathy mad cow disease and Creutzfeldt-Jakob disease in humans.
Prions are terrifying. But what makes them immune to the autoclave?
To understand that, you have to look at how prions break the fundamental rules of biology. Up until they were discovered, we believed that every infectious pathogen bacteria, viruses, fungi relied on genetic material, DNA or RNA, to replicate and spread.
Right, that's Biology 101.
But prions have no genetic material whatsoever. They're simply naturally occurring proteins in the nervous system that have folded into an abnormal pathological shape.
But if they don't have DNA, how do they replicate? How do they infect a host?
They replicate through forced conformational change. When an abnormally folded prion bumps into a normal, healthy protein in the brain, it acts as a corrupt template.
Oh, wow.
It physically forces the normal protein to refold into the same diseased shape, often converting flexible helical structures into rigid, sticky sheets. Those newly misfolded proteins bump into others, setting off an unstoppable structural chain reaction that destroys the brain tissue.
And because they are just rigid sheets of protein with no delicate DNA core, they just ignore the 121-degree steam.
They are incredibly stable. Prions will easily survive a standard autoclave cycle that would obliterate 1 trillion Geobacillus spores. While the heat might damage them slightly, enough of the abnormal structure remains intact to continue acting as a corrupt template.
That is deeply unsettling. You could have a perfectly executed standard autoclave cycle on surgical instruments used in a neurology ward. The biological indicators prove the toughest spores are dead, but that scalpel could still carry infectious prions to the next patient.
That exact scenario is why the World Health Organization and national health agencies had to mandate entirely separate extreme protocols. For any surgical instrument that might have contacted high-risk tissues like the brain or spinal cord, the standard temperature is pushed to 134 degrees Celsius, and the time is often extended to 18 minutes or more.
So sterilization isn't an absolute fixed state of nature. It's a moving target calibrated entirely to the toughest enemy we currently know about. It changed from kills all spores to kills all biological entities capable of replication or infection. Yeah. But if prions are so dangerous, why don't hospitals just blast every single instrument at 134 degrees for an hour just to be safe?
Well, because sterilization is always a delicate balancing act between destroying the pathogen and preserving the tool. Extreme heat, moisture, and pressure are incredibly destructive to materials. If you routinely overprocess stainless steel surgical scissors at 134 degrees for extended periods, the metal degrades, the cutting edges dull rapidly, and the hinges just seize up.
And I imagine a lot of modern medical equipment can't handle heat at all. Things like electronic endoscopes or delicate plastics.
Right. Put an expensive fiber optic scope in an autoclave and you just get a puddle of melted plastic and shattered glass. For heat-sensitive items, we have to abandon the autoclave entirely and rely on chemical sterilants, like ethylene oxide gas or hydrogen peroxide plasma.
It's amazing how much complex physics and chemistry goes into keeping a hospital running safely. But, this science isn't just locked away in medical wings. We actually practice applied microbiology in our own kitchens, right? Let's talk about home canning, because this brings the stakes of the autoclave right into the pantry.
Yeah, anyone who jars their own food is engaging in a high-stakes battle with microbiology, and the ultimate nemesis of the home canner is Clostridium botulinum.
The bacteria that causes botulism.
Yes, it produces botulinum toxin, which is one of the most lethal neurotoxins known to science. It causes paralysis and can easily be fatal. And crucially, C. botulinum forms endospores that thrive in the exact conditions inside a sealed jar. No oxygen, room temperature, and they easily survive being boiled at 100 degrees Celsius.
So if you are canning vegetables from your garden and you just boil the jars in a big pot on the stove, you aren't sterilizing them. You're just giving the botulism spores a warm bath and then sealing them into a perfect oxygen-free environment to multiply.
Which is why government food safety guidelines are so rigid about what you can boil. If you are canning high-acid foods, things like pickles, jams, or certain fruits, you can safely use a boiling water bath.
Because the high acidity prevents the surviving spores from germinating into active toxin-producing bacteria. The acid is doing the work that the heat couldn't.
Exactly. The low pH is a secondary chemical defense. But if you are canning low-acid foods, green beans, carrots, meats, or soups, you don't have that acidic safety net. You absolutely must use a pressure canner.
And a pressure canner is literally just a household autoclave.
It operates on the exact same physics that Chamberlain harnessed in 1879. It's a heavy, sealed pot with a mechanical gauge that traps the steam, raises the ambient pressure, and forces the internal temperature up to 116 or 121 degrees Celsius.
Right.
When we see botulism outbreaks today, they almost always trace back to someone attempting to can low-acid foods using a simple boiling water bath instead of a pressure canner. It is a recurring, tragic reminder that 100 degrees is simply not a universal kill switch.
So what does this all mean? We started this deep dive looking at a comforting, bubbling pot of water, thinking it was the ultimate purifier. But what we've discovered is that achieving true sterility requires a masterclass in physics and fluid dynamics.
It really does.
It's about raising ambient pressure to force water past its natural thermal limits, creating a 121-degree kill zone where moist heat actively dismantles the molecular structure of pathogens. It's understanding the terrifying resilience of a spore's calcium armor, the critical difference between a piece of color-changing tape and actual biological proof of death, and the humbling reality that nature is always innovating, throwing things like prions at us, forcing us to redefine what dead actually means.
And this raises an important question to leave with. We are constantly surrounded by an invisible, everyday infrastructure of sterility. The canned green beans in your pantry, the tools your dentist uses, the glass vials in a vaccine manufacturing plant.
Mm.
All of it relies on this incredibly precise, delicate balance of steam, pressure, and time. It makes you wonder, what other invisible systems of safety are we trusting our lives to every single day, assuming they work flawlessly, that are actually just a few degrees of heat or a few pounds of pressure away from completely failing?
It's definitely a lot to think about the next time you turn on the stove. That boiling water might make a perfect cup of tea, but it is certainly not keeping the microscopic world at bay. Thank you so much for joining us on this deep dive. Keep questioning the mechanisms behind the everyday safety we take for granted. Stay curious, and we will see you next time.